All right, let's introduce the existence theorem for ordinary differential equations. So what I'm going to do is I'm going to write this down. That's not how you spell existence. Existence, and then we're going to leave a blank here. Okay? Leave a nice blank here because we're going to fill in that blank later. Okay? So what this says is, again, like many theorems, we're going to have some kind of hypothesis and some kind of conclusion. So let's introduce what we're talking about. So let's say that, the right-hand side, our derivative, is a continuous function. Remember from calculus class what continuous means. It kind of means the function's all connected. There's no breaks, there's no jumps. There's a more precise definition of continuity as well, with epsilons and deltas that you may have also seen. And then again, we're going to leave oh no. We're supposed to leave a blank right here, actually. Another blank. There's only 3 blanks. All right. That's it. All right. Only one more blank. I'm sorry for messing you up. So suppose this function is continuous in some rectangle, and we're going to call that rectangle R. We're going to write R in set builder notation. R is going to be the set of all ordered pairs t comma y, such that t is between some a and b, and y is between some c and d. Right, so it's just the rectangle where t is between a and b, y is between c and d, and we have that rectangle. I'm just giving that rectangle a name. All right. So that's basically the whole hypothesis. Now we say, if t naught y naught is in the rectangle, then there exists, and again, this is shorthand, you may or may not have seen it, for there exists an epsilon. Oh my gosh, there's actually a lot of curves here. There's an epsilon. This says t is an element. This is the Greek letter epsilon. I know they look similar. They are not the same. All right. There exists an epsilon that's positive, and all right, last blank, and a function y of t defined for all t. And now here's the bad news. I don't have enough room to write it here. Here's the bad news. It's defined for all t, but it's really not defined for all t. It's defined for all t in this interval of t naught minus epsilon and t naught plus epsilon. So the function is the solution, right? We have a solution. I guess I'll finish it. Right, this function that solves the initial value problem. dy dt equals f of t comma y, and y of t naught equals y naught. So this is a lot of words, right? There's a couple of things to talk about. But basically the summary, right, is if the right-hand side of our differential equation, right, if our derivative is continuous in some rectangle, then there's a solution somewhere. The problem is we don't necessarily know, right? Epsilon can be really small, so the solution can really only exist. It's possible that the solution only exists for a tiny amount of time, which could be some problems, but we'll see more of that later. But we have a solution. We basically just need continuity. That's basically all this is boiling down to. Continuity of the slope field, really, means that we'll have a solution in some interval. And again, the interval might be small, might be big, who knows. We'll use that more. We have 3 blanks. We'll do something with the blanks later. A little thing to keep you on the edge of your seat, a little foreshadowing for some fun to come. Anyway, let's use this theorem by looking at an example. So consider dy dt equals 1 plus y squared, and that y naught and t naught are both 0. So this is a really nice function, right? This is our f of t comma y. Because there's no t component, right? We say this is a autonomous differential equation. Because it's autonomous, it's guaranteed separable. Because it's separable, we can solve it by hand, right? All these terms that we have to use here. And we're curious, I guess I'll ask the question, does a solution exist? Now maybe you love calculus and you're like, sure, let me answer that question by just solving this. It's separable. But maybe you're lazy, hypothetically, and you're like, oh, I don't want to do any more work than I have to. We don't need to find the solution. We just need to know whether it exists. Let's use this cool theorem that we have. If that right-hand side is continuous in some rectangle around our initial condition, then yeah, we have a solution that exists for some period of time. So let's check. Is 1 plus y squared continuous? You bet it is, right? I know what 1 plus y squared is. It's a parabola vertically translated up 1 unit. That's a very continuous function. They got no funny business here. It behaves very nicely. All right. So yes, it's in fact, not only is this continuous in a rectangle, it's continuous everywhere. So of course it's continuous somewhere around here because it's continuous everywhere. So we're good to go. So we know a solution exists. We don't even have to find it. We know a solution exists around this point. Cool. It's a little bit more complicated actually to find examples of solutions that don't exist. Even when this theorem fails, right? This is not saying you have to be very careful with a lot of theorems in math, right? Like if your theorem says, right, if A, then B, that doesn't mean not A means not B, right? Like if I say, you know, if like, I don't know, I can't give a great example off the top of my head, but be very careful with your logical equivalencies, right? This is A implies B is not the same as not A implies not B. That's very different things. So be very careful. In other words, what am I really trying to say? I'm trying to say that even if the function's not continuous, there could still exist a solution. We currently don't have a way to prove that there is no solution. We do not have access to those tools yet. We just say, well, if things are nice enough, we know there's a solution. Otherwise, we don't know anything. If you remember your second derivative test from Calc 1, this is essentially equivalent to saying, you know, if that second derivative equals 0, we don't know anything. All right. So I will also ask you another thing. I'm going to ask you to plot the slope field. And again, using technology. You're not going to have to plot slope fields by hand in this class. So we go over to our slope field calculator. I'm going to say, all right, I use dy dx, so I don't have to change anything. And then we'll plot it and say, this is just 1 plus y squared. What does that look like? We can see the slope field. 1 second. All right, and let's look at the slope field for a second. Now, what you might notice is that as x is getting bigger and bigger, we have, wait, hold on. Yeah, as our input, which is t in this case, right, it gets bigger and bigger, the slopes are getting bigger and bigger. But yeah, it doesn't look like anything crazy is going on. So yeah, you know, looks fine, looks fine. But let's actually find the solution. And this is, again, just practice solving separable differential equations, practice doing integrals. I want you to pause the video right now, do all the steps, separate this out. And again, be very careful with the first step. Whenever you have an autonomous differential equation, your first step is dividing both sides by that right-hand side if it's autonomous. So you should get 1 over 1 plus y squared dy equals dt, and that's what you integrate. You don't subtract anything over. You have to divide. For all separable differential equations, you're only dividing to get things separate. So this is what you're actually integrating both of. But anyway, so pause the video right now. Once you've paused the video and solved this out, you should get that y is equal to tangent of t. And that's it. All right, it's t plus c, but your initial condition means c is equal to 0. So our solution to this differential equation is tangent. And so yes, a solution exists, but a solution does not exist for all time. In fact, right, as soon as t is pi over 2, we have some serious problems. That doesn't exist. Okay, so we do have a solution, but it only exists for some amount of time. Again, our initial condition was 0, 0. The solution stops existing at pi over 2. And if we have negative time, it stops existing at negative pi over 2. So again, this is what that theorem's saying, right? Is that we can guarantee some existence, but it's only for some window of time. Now, what is the extendability of that solution? That's another question that we'll talk more later. So be very careful. This doesn't guarantee a solution for all time. And that'll pop up a little bit more with physical models. Specifically, right, if you do have a solution that looks like this, something crazy is happening as t is getting close to pi over 2. Now, maybe that means there's a problem, like maybe your model is not accurate near pi over 2, and that's okay. Maybe something physically crazy is happening at pi over 2, okay? But it's definitely going to be drawing your attention to, okay, what is happening near this point? Because something crazy is happening. That's what we always want to think about when we are describing those physical systems. But anyway, that's the basics of existence. We'll talk about uniqueness in this next video, and then the cool things that we can do with uniqueness to finish out this section. Good luck and bye-bye.